Every nuclear weapon begins with a simple idea: splitting an atom. But the journey from raw rock in the ground to the most powerful force ever unleashed by humanity is one of engineering, physics, and irreversible consequences. The search for uranium begins with science. Geologists first read the landscape from above, using remote sensing like airborne gamma-ray spectrometry to detect radioactive signatures. This creates a map of possibilities. The next phase is ground truthing, where field teams use handheld scanners to verify the data and pinpoint promising areas. To get a definitive answer, drilling rigs extract long core samples. These are sent to labs for chemical analysis, confirming the uranium's concentration and economic viability. Only after this rigorous process can a potential mine site be identified. Once a deposit is confirmed, the geology dictates the extraction method. For large, shallow deposits, open-pit mining removes surface layers to access the ore. Deeper veins are followed through underground tunnels. A third method is in situ recovery, or ISR, used when uranium is in porous sandstone. A solution is circulated to dissolve the uranium, which is then pumped to the surface, leaving the rock largely undisturbed. Regardless of the method, safety is paramount. The industry operates on a principle of people first, data always. This means robust ventilation, remote-controlled machinery to minimize exposure, and constant water management. Every worker wears personal dosimeters to monitor radiation, ensuring safety is a continuously measured reality. The responsibility extends far beyond the mine. Before work begins, environmental baseline studies establish a benchmark for restoration. During operations, all material moves to controlled facilities. Water is continuously tested at monitoring wells. Waste rock and tailings, the leftover material, are stored in specially engineered, multi-layered containment facilities to prevent contamination. The ultimate goal is full land rehabilitation. A detailed closure plan is in place from the outset, ensuring the land is returned to a stable and safe state, fulfilling a commitment to the environment and local communities. Once extracted, the raw ore begins its transformation at a milling facility. The first step is purely mechanical. Massive crushers and grinders reduce the rock to a fine, sand-like consistency, maximizing the surface area for the next stage. This slurry is then subjected to a chemical process called leaching, where a solution dissolves the uranium, separating it from the waste rock. This uranium-rich liquid then undergoes further purification through solvent extraction or ion exchange, meticulously isolating the uranium from other dissolved minerals. Finally, it's precipitated out of the solution, dried, and heated. The result is a stable, concentrated uranium oxide powder known as yellow cake, a name derived from its historically vibrant color. Each batch is rigorously tested for quality before being packaged into sealed, barcoded drums, ready for the next leg of its highly controlled journey. From the mill, this material enters a strict chain of custody. Every drum is weighed, sealed with tamper-evident tags, and logged. International Atomic Energy Agency safeguards provide an additional layer of verification, ensuring every gram is accounted for. These tracked shipments arrive at a secure conversion facility, where the yellow cake undergoes its final chemical change before enrichment. Here, the solid powder is converted into uranium hexafluoride, or UF6, a compound that conveniently becomes a gas at a low temperature. This conversion is a critical step, as the gaseous form is essential for the enrichment process that follows. Throughout this entire journey, from ore to gas, the focus remains on control, verification, and safety. This isn't just industrial chemistry, it's a system of global accountability, setting the stage for the delicate physics of enrichment, an exercise in separation, not creation. The core principle of enrichment isn't about creating energy, but a delicate act of separation. Natural uranium is mostly composed of two isotopes, uranium-238 and the much rarer, fissile uranium-235. They are chemically identical, but U-235 is slightly lighter. Inside a gas centrifuge, uranium hexafluoride gas is spun at incredible speeds, generating immense centrifugal forces. The heavier U-238 molecules are pushed towards the cylinder wall, while the lighter U-235 molecules concentrate closer to the center. It's a process demanding extraordinary engineering precision, where components spin faster than the speed of sound. A single centrifuge only achieves a minuscule degree of separation. So in practice, thousands of machines work together in long, interconnected cascades. The slightly enriched gas from one stage becomes the feedstock for the next, while the depleted stream is fed back to an earlier stage. Each step nudges the composition a little further. This entire system is incredibly energy-hungry, and its stability is paramount. Everything is constantly monitored: vibration, temperature, and power draw, with automated alarms and redundant systems ready to intervene at the slightest deviation to keep the entire cascade on target. The output is a spectrum of possibilities. Low-enriched fuel, typically under 5% U-235, is used to power civilian nuclear reactors under strict international oversight. But as enrichment levels increase, so does the potential for misuse. Any material enriched to higher levels is subject to the most stringent controls imaginable, tracked with unique tamper-evident seals, verified by international inspectors, and accounted for through meticulous audit trails that safeguard against any diversion. At the core of nuclear technology is fission. When a neutron strikes certain atomic nuclei, the atom splits, releasing energy and additional neutrons. If controlled, this reaction produces electricity. If uncontrolled, it releases energy almost instantaneously. During World War II, two fundamentally different nuclear weapon concepts were developed, each based on distinct physical principles. One relied on rapidly combining nuclear material. The other used symmetrical compression to initiate a reaction. These designs are now studied historically, not as blueprints, but as lessons in physics, ethics, and responsibility. The first nuclear detonation permanently altered history. Scientists understood the theory, but even they couldn't fully predict the consequences. From that moment forward, humanity possessed the power to end itself. The effects of a nuclear explosion unfold in zones: intense heat, shock waves, radiation. The damage isn't just physical. Survivors carry the effects for decades. This is why nuclear weapons are not just engineering achievements, they are moral warnings. Understanding nuclear science isn't about learning how weapons are made. It's about understanding the implications of nuclear force. If this helped you understand the science behind the most powerful force on Earth, subscribe for more original content. If you have any questions or comments, please leave them below. Your input matters. Share your ideas for our next video in the comments, and we'll recognize your contribution. Thanks for joining us on this exploration of the fascinating stories behind everyday things. Don't forget to like, subscribe, and stay tuned for more captivating content. Thanks for watching, and if you want to learn more, click the next video right here.